Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will talk about the concept of covariance matrix of a random vector, and then we will apply this concept to find the covariance matrix of beta hat and epsilon hat, okay? Where epsilon hat is our vector of residuals. Well, let's begin. As I said, first I would like to discuss with you the concept of covariance matrix of a random vector. So we're going to start with a simple example, a 2x1 random vector, but what we're going to be discussing here can be easily be extended to another vector of any dimension n by 1. Okay, so it's just that it's going to be easier for us to see it here on the screen. But the ideas again can be easily be generalized. Okay, so we know that random vector is just a vector that is formed by a bunch of random variables as its elements. Okay, so in this case we have a 2x1 random vector, so that means that first element, second element of that vector are random variables. Okay, now we also know how the expected value of a random vector is defined. The expected value of a random vector is just we compute the expected value of its elements, and we form a vector with the right dimension using those expected values. Okay, so in this case, naturally the expected value of a random vector y must be a 2y1 vector, and it's just the expected value of y1, and the expected value of y2 would be the second element of that vector of means of expected values. Let me use this notation, mu1 and mu2. Mu1 to refer to the expected value of y1, similarly for mu2, expected value of y2. Okay, so if we compute the difference between y and its expected value, clearly it's just going to be y1 minus mu1, y2 minus mu2. Okay, so it's just the the sum of vectors works like that, right? You do an addition element wise. So if it's a difference, it's the same thing. Okay, you proceed element wise. Okay, so now we are aware that this guy is 2y1, so the transpose of that vector is going to be a 1 by 2 vector, okay, with y1 minus mu1 as its first element, y2 minus mu2 as its second element, right? Easy. Now, note that if we compute this product, y minus expected value of y times y minus the expected value of y transpose, this guy is 2 by 1 and this guy is 1 by 2. So we can compute the matrix product, right? These dimensions work to compute a matrix product, but the result, right, it's going to be a 2 by 2 matrix, right? Makes sense? So the first one, it's going to be the first element of that 2 by 2 matrix is going to be y1 minus mu1 times y1 minus mu1, y1 minus mu1 square, right? The second one would be y1 minus mu1 times y2 minus mu2, right? That would be the element on the first row, second column, because this is the first row and this is the second column, so it must go here. And we proceed in a similar way for y2 minus mu2 times y1 minus mu1. That's going to be the element on the second row, first column. It's that cross product here. And then we have y2 minus mu2 times y2 minus mu2, clearly y2 minus mu2 square. But again, can you see that we ended up with a 2 by 2 matrix, right? So the order here in this product is important, because if we had it backwards, if we had a transpose here, then and nothing here, then instead of being a matrix, we would have a scalar, right? That's what mathematicians call that, meaning just a number. It would be a 1 by 1 matrix. So just a number, right? Anyway, so be careful with the order here. Be careful, because when we talk about the covariance matrix, now you can see that it's going to be a matrix, because it's the expected value of that 2 by 2 matrix, in this case, that we just computed, right? It's a 2 by 2 matrix, and we want the expected value of that matrix. So you know, the expected value of a random matrix is defined in a similar way. It's just the expected value of its elements, and its elements are going to be random variables. Okay, so from this, right, we can see that the covariance matrix is in this case a 2 by 2 matrix, and that if you compute the expected value of the elements, hey, this is just by definition the variance of y1. This guy here is just by definition the variance of y2. And here we have the expected value of these interesting cross products. Note that these are going to be the same, right? The expected value of y2 minus mu2 times y1 minus mu1, it will be the same as the expected value of y1 minus mu1 times y2 minus mu2. And this has a special name. Remember it? This is the covariance between y1 and y2. Okay, so that's why well, we refer to this matrix as the covariance matrix. Okay, and the covariance matrix of a vector is exactly that, a matrix. Okay, in our case, we had originally a random vector. The dimension of a random vector was 2 by 1. Then we ended up with a 2 by 2 matrix. On the diagonal, again, we're going to have the variances, and on the off diagonal, the other elements not located on the diagonal will have the covariances, right? Okay, so keep that in mind. Now, I have presented you this definition and an example of the definition of covariance matrix for a random vector. Note that if instead of having just a random vector with only 2 elements in it, right, with only 2 entries in it, if we had, say, I don't know, a 4 by 1 random vector, right, we would have 4 of these, mu1, mu2, mu3, mu4. We would have 4 elements as well in this vector of differences. When we computed this product, y minus its expected value, y minus its expected value transpose, instead of having a 2 by 2 matrix, we would end up with a 4 by 4 matrix. And then when you computed the expected value of that 4 by 4 matrix, On the diagonal, you will have the variances for y1, y2, y3, and y4, and on the off diagonal, right, the off diagonal elements would contain all the possible covariances, and this matrix, the covariance matrix, is clearly a symmetric matrix, right? It's symmetric, it's transpose, it's going to be the same as itself. Okay. And again, if instead of 4 entries we had n, same idea, right? Let's keep going. So at the beginning I said I would like to use the concept of covariance matrix to find the covariance matrix of beta hat and epsilon hat. Beta hat, you know, our vector with the estimators of the beta parameters. Epsilon hat is going to be our vector of residuals, okay? And I would like to find the covariance matrix of the vector of residuals. Okay. So just like last time, remember that we talked about a proposition that we used to show that the expected value of a beta hat equals beta, meaning that beta hat was an unbiased estimator of beta. Well, now we're going to need a similar result, a similar proposition, but about the covariance, so we can derive the covariances that we are interested in. Okay, well, here's the result I would like to use, and we're going to show that result again in a particular way, but general way. And the only restriction is the dimension of the matrices that I'm going to be using, but again, the same rationale can be applied and the conclusion holds. Okay, anyway, so the proposition is given in general terms, so we have just a matrix A with constants. It is not random. Okay, dimension r by n. We have a vector of constants r by 1, and we have a random vector y m by 1. Those are the dimensions of y, and then we would like to find the covariance of a new random vector, a transformation, right? And how we obtain that transformation? Well, we just multiply y by that matrix A, and then we add that vector of constants C. Okay, it turns out that the covariance of A times y plus C equals A, the matrix A, times the covariance matrix of y times A transpose. Okay? Okay, so let's proceed step by step. Carefully, you'll see that it's going to make sense. First, let me define W as AY plus C. Okay? So, using what we know from the other video where we showed that beta hat is an unbiased estimator, right? We know that the expected value of W is going to be the expected value of AY plus C, right? But then we know that we could factor out that matrix of constants A times the expected value of y, and we know that the expected value of a constant is a constant, so we do that for each of the terms that define that vector C, and we have this, right? Okay, so that you have seen before. Now, here we want to find the covariance matrix of this, right? So, well, we want to find the covariance matrix of AY plus C, so meaning the covariance matrix of W. So the way that we have to find the covariance matrix of something is applying the definition. So let me compute W minus the expected value of W. Now we have it. So it would be the difference between AY plus C minus A times the expected value of Y plus C. So that negative sign is going to affect both terms here. So that means that that C is going to cancel out. So we only have AY minus A expected value of Y. Again, bear in mind that A is a matrix, okay? But these are the same vectors, so they cancel out, and we're going to be able to factor out that matrix A, okay? So this is just going to be that matrix A times Y minus the expected value of Y. We factored out that matrix A. Okay, now as I said, we would like to apply that definition. Remember that the definition is going to be the expected value of W minus the expected value of W times W minus the expected value of W transpose. So we want the expected value of that product, okay? So here I remind you that that's how we define the covariance matrix of a random vector W. In this case, I'm calling it its expected value of that product. Okay? And remember, first you have just that difference, then you have that transpose. So it's going to be a matrix. Here I'm just plugging in what we had, right? What we derived here together. So W minus expected value of W is the same as matrix A times Y minus expected value of Y. Okay? If we take the transpose, this is the transpose of a product, is going to be transpose of the second term times transpose of the first term here, right? First matrix. Okay. Now, well, the expected value is going to allow us to just factor out that matrix A on the left, but also on the right. That's a property of, you know, the expected value of this matrix multiplication that we have here. And if you want to show it, it would be in a similar way to what we did on that other video, right? Where we showed that property, the linearity of the expected value. Okay? Okay. So, now note that, hey, take a look at this. A times expected value of Y minus expected value of Y times Y minus expected value of Y transpose times A transpose. What's this? This is the covariance matrix of Y by definition. So in the end, what we have is A times the covariance matrix of Y times A transpose. And that is exactly what we wanted to show, right? So note that here, right, I didn't say anything about the dimension of A or Y or anything. So what we did here together, that holds as long as, you know, this matrix product is legal, okay? And as long as this vector C has the right dimensions, okay? So the only part where we kind of did it with a simple example was when we were trying to really understand the definition of the covariance matrix of Y. But you know, this was just very general. Okay, so we have shown that the covariance of A times Y plus C equals A covariance of Y times A transpose, right? And it wasn't that hard. It was just we had to be careful in applying the definition of covariance matrix of a random vector. Excellent. So now that we have that proposition in place, we are going to be able to find the covariance of beta hat and the covariance of epsilon hat. Let me open another one of these. So before we find the covariance matrix of beta hat, let me remind you something. This is a result from linear algebra. Recall that if you have a matrix B and you compute its transpose, and then you want to find the inverse of this guy, then that's the same as B inverse transpose. Okay? Make sense? Okay. Another thing, we have to recall the expression for beta hat. You have seen it before since we started, well, even when we talked about simple linear regression, we used, even back then, this kind of expression for beta hat. Remember? Okay. And it turns out that that beautiful expression holds in general, right, for multiple linear regression as well. Okay. So, what we said is we would like to find the covariance of beta hat. And we know that this guy, in general, right, it's going to have, I don't know, say k unknown parameters, okay? So let's take a look at that expression. We know that we would like to use our proposition, the one we just showed. So if we think about x transpose x inverse x transpose as a matrix A, then beta hat is just A times Y. Matrix of constants, that's important, right? Times the random vector Y. Okay? So no problem. Using our proposition, let me remind you what it says. If you have the covariance of A times Y plus C, that equals A covariance of Y times A transpose. Okay? So we have here, that would be the same as the covariance of A times Y but by our proposition, what we have there is just A times covariance of Y times A transpose. Now, something that we're going to need then is the covariance of Y, right? And if you think about it, the way our model is defined, it looks like this. our model will look something like this. Our vector of observations, it's going to be x times beta plus vector of random fluctuations, right? So what we want here is the covariance of y. So note that that would be the same as the covariance of x beta plus epsilon, right? But this is just a constant, right? So it's going to be just the covariance of epsilon, right? Now let's think about the covariance, and remember, when we write this down and epsilon is a random vector, we are saying, oh, it's not just a plain covariance, it's not just a number, it's a covariance matrix. And since epsilon has dimensions n by 1, we have n observations, so the error vector will be also n by 1, just like this guy here. Think about it. The assumption is that the errors have mean 0, right? And variance sigma square, right? So if we go back to what we had here, when we talked about how we define covariance matrices, what we said is on the diagonal you have the variances. So in this case, the covariance of epsilon, the vector epsilon, is going to have a bunch of sigma squares here on the diagonal. And what we also know is that the epsilons are assumed to be independent. And if we have two independent random variables, the covariance is 0 between them, right? So we would have sigma squares here and zeros elsewhere, right? So one nice way of expressing that would be, you have sigma square times an identity matrix, an n by n identity matrix. Make sense? Okay, so now we have the covariance matrix. So we have A times sigma square times the identity matrix times A transpose. Okay. Now that sigma square, that's a constant. So we're going to be able to factor it out. You know, just when you're doing that sort of a matrix multiplication, you can show that you can factor that constant out. So we have sigma squared here, and then we have the identity times A transpose. It's going to be just A transpose. So we have sigma squared times A transpose. And then we're almost there. Now remember how we defined A? A was this, right? So let's plug in what A represents. So we have A here, we have sigma squared. Now we need the transpose of this matrix here. Something like this. Oops. Capital T, that's better. So we're almost there. Now, using what we know about the transpose, we have a product of two matrices transpose, then it's going to be the transpose of the second matrix times the transpose of the first matrix. So let me write that down. So that's just going to be X, right? Transpose transpose, it's going to be X, right? And then we're going to have this guy, X transpose inverse transpose, right? Okay. Agreed? But note that here what we have is X transpose X inverse times X transpose X. That's going to be just an identity matrix. So sigma squared. Then we're going to have an identity matrix there. Oops. Times this. But now, remember that at the beginning I said, recall that if you have a matrix such that you have B transpose inverse, that's the same as B inverse transpose. Okay? So, thing is that these, transpose and inverse, can switch places. Right? So that's exactly what we're going to have here. Right? And then when you do this, X transpose X transpose, guess what? You end up with X transpose times X transpose transpose, which is just X, right? So in the end, you will have just this. Times the identity matrix, it's that, and that's it. Okay? Make sense? As a homework problem, what you could try is seeing that if you do this for the simple linear regression, it's going to work. Okay? And remember that, for instance, when you use a centered model, then X transpose X is going to be diagonal, so finding that inverse is going to be easy. But if you have the classical simple linear regression model, right, then, well, it's not going to be easy to find that that easy. It is not impossible, it is doable. But then you're going to be able to very quickly find the covariance between the parameters beta 0 and beta 1, okay, with this expression. So anyway, what we have done here is we have found the covariance of beta hat. Let's do something more. Let's take advantage of the result that we have shown, right? And let's find the covariance for epsilon hat. Okay, so epsilon hat and remember that we could find the residuals using the H matrix, okay, like that. The identity minus H times Y is going to give you the residuals. Now what we want is the covariance of that guy, right? So we want the covariance matrix of our residuals. So that's the covariance of this, a matrix, times Y using our proposition, right? Using our proposition, what we have is matrix times covariance of Y times matrix transpose. Just like before, the covariance of Y equals sigma square times the identity. So I have I minus H times sigma square times the identity. And remember that we showed that I minus H is symmetric. So instead of I minus H transpose, we get to write I minus H. And then, just like before, we get to factor out that constant. Let me pull it out. Identity times I minus H, I minus H. But we also showed that I minus H is idempotent, right? Remember? So I minus H times I minus H is I minus H, right? Again, this is because remember that we showed when we talked about the hat matrix and about influential observations that I minus H is symmetric, and this step here is because I minus H is idempotent. Okay, so the covariance matrix for the residuals is sigma square times the identity minus H. Now, let me just make a note of something here. Remember that at some point we derived the variance of the residuals because we wanted to standardize in a more appropriate way, right? So we found the variance of the ith residual and we came up with studentized residuals, right? So anyway, that's why we needed the variance of the ith residual. So note here that this guy contains variances and covariances, okay? So note that the diagonal elements of this guy well, the diagonal elements are, you know, the variances of, let me say, epsilon 1 hat epsilon 2 hat and so on, right? The individual residuals, right, for each of our observations. Before we call them E, right? You call them E1, E2, and so on, right? Just using a slightly different notation here. It's the same. What I want you to bear in mind, regardless of the notation that we're using, is that the residuals are just our way of estimating the actual epsilons, the random fluctuations, right? Okay. So since we have this sigma squared times I minus h, and that's the covariance matrix, the diagonal elements of I minus h are just the diagonal of, the identity is just 1, and the diagonal element, the generic diagonal element of h, say that it was the ith diagonal element, that's hi, right? So the variance of epsilon I, well, epsilon hat I, or if you will, the variance of EI, the ith residual, is just 1 minus HI times sigma square, right? Just like before. But now with this approach, it's more elegant and it was faster to get, right? Okay. So let's summarize what we did here together. What we did here together is we introduced the concept of covariance matrix of a random vector. Then we applied a proposition related to the covariance matrix of a random vector. To be more precise, what happens when you transform a random vector with a linear function that looks like this: a matrix A times your vector, random vector y, plus a constant, well, a vector of constants c, right? Then what you end up with is A times covariance of y times A transpose, and we applied that proposition to find the covariance matrix for beta hat and for epsilon hat. Okay, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.